Hello, Flat Earth researchers, debaters and debunkers. Nick Davies here, Phuket Word. You might hear frogs in the background. They're just chilling in the pond in the garden, which is rather apt because I want to talk about the relationship between water and gravity. This was prompted by watching a documentary called The Deepest Breath on Netflix at the moment. It's about free divers, and it focused on a few record breakers, and we'll come to some of the comments they made a little bit later on. But first I wanted to talk about gravity and really ask whether it's such a big deal, and should we be overly concerned with thinking about the cause of gravity. Because, of course, when you think about a globe, gravity is integral to that globe because you need some way of sticking to the outside of a spherical Earth, which you know would be otherwise physically impossible if you didn't have something doing that. So it's a big deal for the globe. But when it comes to living on a level Earth, then why do we need to place any focus on up and down? It kind of is what it is. We already have, I suppose, surrendered to the understanding that we don't know who we are really, where we are, how we came to be, what created this, but we are in an intelligently designed environment, and we live in a space that's most suitable for us. So of course most of that happens in the air, and we do spend a lot of time in the water as well, and we can adapt to being in the water to a great extent. But being in the medium of air is where, of course, all our original measurements of gravity came from, using masses that were more dense than the air. And I don't think there's any need to look any further than the medium in which we find ourselves in for the cause of gravity, or what basically keeps us on the ground for the most part. Because take, for example, the fact that our metric system is based on taking 1,000 cubic centimeters of water and then weighing it in the air. And that will give you a kilogram, or 1 litre. So 1,000 cubic centimeters in volume, or 1 litre of water, is equal to 1 kilogram, 1,000 grams. So there you have your foundation for all your measurements, yeah? And okay, so you can talk about that in terms of acceleration if you like to. It will weigh the equivalent in newtons, if you like. You just converted it to talk about a force as 9.8 newtons, because you're imagining that it's being pushed or pulled down towards the ground with the same amount of force that would take to move that object in a certain direction over a certain distance and time, 10 meters in a second. Yeah, so how much force cumulatively do you need to push that object that far in that amount of time? That's how you measure the weight. And so yeah, you get a kilogram, or 9.8 newtons of acceleration, as it were. But so what? That's all fine and dandy. And it's only because we find ourselves in the medium of air that we can do this. When I first started looking into this, I would take scenarios in my mind that are all happening in the air with lots of different elements, and then transfer that whole scene to being underwater. And of course, you know from your own practical experience that things behave differently in the water than they did in the air. So we know, for example, that you can make an egg sink or float in water depending on the relative density, or by changing the density of the water. You put an egg in normal water, plain water, and it will probably sink to the bottom if it's a good egg. But otherwise, if you add salt, for example, to the water, then that egg becomes more buoyant and it might float around halfway, and then you could even add more salt and make it float all the way to the top. Because the water is then much denser than the egg. So what's really happening there is there an external force pushing or pulling or doing anything other than what's going on within the medium? A couple of things to mention here is that, these two mediums of air and water or anything else don't truly mix, but water will envelope a mass, yeah, and that mass might be a mass of air, and that's a bubble, of course. So why is a bubble the shape that it is? Is it because the gas is naturally forming that shape? Well, partially, but also at the same time, the water is squeezing on that bubble. It's keeping all that air compressed. They're not going to mix. It's not the bubble's not going to explode and then mix into the water. They just don't want to mix these two different mediums. And so there is this really, really, really strong force between, or, you know, keeping the water together as well as keeping the air together. You see what I mean? So think about that the medium itself is squeezing the mass, whether it's a less dense or a more dense mass. So if we're in the medium of air, we're on the ground, okay? So we apparently have about 101 kilopascals of air pressure pushing on us when we're standing at sea level. Obviously there are these layers of density, or this density gradient, and so the air gets thinner and less dense as you get higher. Again, there's no need to attribute a cause to that. It is what it is, and obviously being much less dense than us, we will go through it. But are we being pushed to the ground? Because we know that the air around the surface is quite dense. For example, that Red Bull jump from the stratosphere, or whatever they like to call that layer of air, was a lot less dense, and as he came closer to the ground, he apparently slowed down, so he was being cushioned by the more dense air as he got close to the ground, but of course would still end up coming through it to the ground. And then when you're on the ground, you've got all this pressure of the air around you and above you, which is apparently equivalent to about just over a ton, 1.1 tons of weight on you, on your head and shoulders, pushing you down to the ground with air pressure from all the air above and of course the pressure around you. Again, keeping in mind that although we can walk through air, and you can put your hand through water, or a submarine can go through it, that water or the air will always hug you or hug the object that's going through it. So it doesn't actually cleave apart, it just lets it through. So it's very malleable in that sense, but never gets actually separated. So again, there's a very strong force keeping the water molecules together, or however you want to envisage it, the same as the air molecules. So are we being pushed? Just to give you an example of something that I thought about was when you take a bottle of Johnson's baby shampoo. Get a big bottle if you can. And the reason I recommend this is because it's not a plug. It's because it's a very clear bottle, transparent bottle, in which you can see the yellow liquid inside, and it's a very viscous or thick liquid. So when you turn the bottle upside down, the bubbles that were in the lid, they slowly make their way up to the top. And as you watch these bubbles, they have a teardrop shape. So it's as if the medium, the liquid, is squeezing on these bubbles and pushing them up. And it happens very slowly, so it's fascinating to watch. So go out and invest in a bottle of baby shampoo to see that effect. So that leads me on to some of the slides and the comments made in this movie or documentary, The Deepest Breath, where you've got these freedivers going down to around about 100 meters. And in one of these sections of the documentary, one of the divers, a female diver, talks about the experience. And you can see that it says here, after 30 meters, the pressure pushes me down. So obviously there's a bit of a struggle to swim down that first 30 meters, but apparently the pressure then changes what happens, and it starts pushing the diver down. And they actually talk about it as being the free fall. So they don't have to do any more swimming. They are literally falling through the water because they've reached a point where the pressure is now enough to push them down rather than pushing them up or keeping them buoyant. So can we equate what we see here and know from these divers' experience to the air? Is the same thing happening in the air? Of course, when we're talking about relative density, then the volume of an object is integral to the direction it will take, whether it's up or down in any given medium. It also depends whether the volume is fixed or flexible. For example, the diver in the documentary said that the further she goes down, the more compressed her lungs become until they're about the size of her fist. So in effect, she is becoming more dense as she experiences more pressure around her, and so she continues to fall. Likewise, as you get higher towards the surface, then the lungs expand again. And of course, that continues when we get into the air. If we're going to send up a helium balloon, we need a lot of space for that helium to expand as it gains height. So it starts off very flappy and loose on the ground, but as the balloon gains altitude, the helium expands, and so does the volume of the balloon. And this creates this change in the equilibrium. So you have this attempt to equalize the pressure between the object and the medium it's in, which gives rise to the rise, as it were. So this isn't really anything to do with any external force other than the relationship between the object, its density and volume, and the medium around it. If, on the other hand, though, you take an object with a fixed density and a fixed volume, such as a steel ball bearing, it cannot expand or contract with the changes in the pressure of the medium around it. So, being a dense object with a fixed volume, it will always fall through the air, and it will also fall through most liquid mediums, depending on the viscosity. That will make a difference to the speed at which it goes through the medium, or is squeezed through the medium, if you like. But then, if you put a ball bearing in mercury, which is a liquid medium, the ball bearing will float on that liquid mercury. So we still have this relationship between relative density and volume. And that's as far as we can tell or measure any so-called gravity or directional vector on the Earth. What's beyond that is unknown, and we don't necessarily have to postulate about any other external forces when we have this direct relationship between the relative density and the volume of an object, and what that object comprises of and how flexible it is within any given medium on the Earth that we can measure. Food for thought, I hope. Thank you very much.